VLSos here. This is a video lesson on solving systems by graphing. In a previous lesson, we learned that a system is a problem that involves more than one equational relation at the same time. For example, we could have the equation y is equal to x plus 3, and the second equation, y is equal to negative 2x plus 6. This problem involves two equations. We have a bracket that ties those two equations together so that we're being shown or told that we want to consider these equations at the same time, which means that if we're going to find a solution, we need to find values for both x and y, numbers for x and y that make both of these equations true at the same time. Now, finding a solution to a system can be fairly sophisticated. One relatively easy way to go about it is to graph both of these equations and look for solutions where the equations intersect, if they intersect at all. We're going to graph these two equations. They're both lines. I'm going to set up axes, a number line for x and a number line for y. There are several strategies to graph a line. One reliable way is to make a t-table of points. Choose values of x and calculate values for y using the equation. But there are two equations. Let's do the first in this t-table. If I choose a few values for x, like 0, 1, and negative number, negative 2, we put 0 into this equation for x. 0 plus 3 makes the y value of 3. Substituting 1 in for x, 1 plus 3 is 4. And negative 2 in for x, negative 2 plus 3 is 1. This gives me a few points to graph. 0, 3 is here. If I make a tick mark at 3, 1, 4, negative 2 on the x-axis, 1, and all we need is a couple few points to graph a line, so I can draw the entire graph of the line by connecting those points. But we have a second equation to graph. We would need a separate t-table, choosing values of x. Now, these values of y for the second equation are going to be different. Different values of y, different equation. Very often, when we have two equations and two different y values, one, we will put a 1 and a 2 to distinguish between those two y's. We have y with a little 1, or y sub 1, and y with a little 2, or y sub 2. So when we fill out our t-tables, we can distinguish between the two with those symbols. Now, if I choose values of x here, I will be using a different equation to calculate y. Putting 0 into this y sub 2, or this second equation, I get negative 2 times 0 is 0, plus 6 is 6. Putting 1 in for x, I get a y value of 4. Putting 2 in for x, I get a y value of 2. There are other ways to speed up graphing. I might have recognized that both of these equations are in slope-intercept form. Slope-intercept form is y equals a number times x plus a number, or y equals mx plus b. b is the y-intercept. In the second equation, I have a y-intercept at 6. That confirms that this point on the t-table is the same location. I have a slope of negative 2. That means I go down 2 and over 1 to get to this point. I can continue to use the concept of the slope to draw more points. Connect those points to graph that second equation. Now let's consider a solution. Well, any point that lies on any of these lines is a solution for that single equation. But what I'm asked to find is a solution to the system, which means a value for x and y that makes both equations true at the same time. There's one point that is on both lines. There is one point that represents the solution to the system. It's the point of intersection here. We'll point to it and call it an intersection. The coordinates of this intersection are the x and y value, an x value of 1 and a y value of 4, or the coordinates 1, 4. The first, of course, the first number is the x value, the second number is the y value. This intersection, the coordinates of this point, is the solution to the system. And we can say in general, for systems, any point or points of intersection are solutions to a system. And a solution is values for variables that make the equations true. In this case, we have two equations, and we can confirm that the value 1 for x and 4 for y will make these equations true, both of them at the same time with the same values. We can take this first equation, y or 4 should be equal to x or 1 plus 3. And 4 is indeed equal to 1 plus 3. But at the same time, y, again 4, should be equal to negative 2 times the value of our x, which is 1, plus 6. Is that true? Well, negative 2 times 1 is negative 2. Negative 2 plus 6 is 4, and it's equal to 4. So we can see when we substitute these values for x and y into both equations, it makes both equations true at the same time, so we've confirmed that that point is a solution.